pleasure to welcome and introduce Professor Junji Kido from Yamagata University. Junji was born in Osaka, then did his undergraduate work at Waseda University in Tokyo, and then his master's and PhD at Polytechnic University in New York. He's been with Yamagata University since 1989, where he's currently one of the big leaders. He's been a pioneer in the field of organic light-emitting diodes. Especially, he was one of the first ones to push the concept of using organic light-emitting diode technology for solid-state lighting. And one of the big seminal paper in this field is the paper he published in 1995 in Science, where he was, a visionary, claiming that that technology someday might have some applications. And at the time, I checked the paper. He demonstrated a luminance of 2,000 candelas per square meter at what he called the low voltage of 16 volts. And the luminous efficiency was 0.5 lumens per watt, which at the time was absolutely remarkable, defined the state of the art. And so today he will share with us some of the recent progress and discuss the latest achievements and things that moved a very long way. And so we're extremely pleased and honored that you're visiting again and share with us some of the latest achievements. So please join me in welcoming Professor Kido.
Okay, good afternoon, ladies and gentlemen. Well, thank you very much, Bernard, for your very kind introduction. My name is Kido. I'm from Yamagata University, Japan. As he mentioned, I've been working in this field, in the OLED field, for I think more than 26 years. So you can guess how old I am. Today, I will show you what we have done and what we are going to do. All right. Okay, this is Japan. Okay, maybe many of you don't know where Japan is. Okay, we live in Ireland. Okay, this is Japan is in the Far East. Okay, it's not part of China. This is Japan. This is main island. Hokkaido, Kyushu, Okinawa, and here Tokyo. You know Tokyo, right? Then you go north. It takes about 2 hours to get to our city, Yonezawa. Okay, this is here. So we're in the middle of mountains, okay? So we have lots of trees and volcano and cherry, hot spa or whatever. We have lots of natures. Now, Yamagata is famous for its OLED, okay? We have OLED factories, 2 factories in Yonezawa city. One is for display, the other is for lighting. All right, this is the outline of my talk. First, let me talk about displays. Okay, you use LCD displays. In the future, in the near future, you will use OLED displays. Then, white OLEDs for lighting. Now you use maybe conventional fluorescent lamp or LED lamp. In the future, you're going to use OLED. Okay, first displays. All right, this is OLED structure. Very simple. Okay, organic semiconductor, we have P-type, N-type, and emitting material. So we have this kind of structure, P-type, emitter, N-type. Okay, then if you use blue emitter, you get blue light. You use green emitter, you get green light. Very simple. Then also, it's kind of area light source. Okay, then it's very thin. How thin? The total thickness of OLED is like typically like 300 or 400 nanometer thick. So it's very, very thin. So compared to substrate itself is like a 0.4 millimeter something. So it's extremely thin. So you need some kind of support. That's why we need substrate. Okay, so substrate itself could be glass or plastic. If you use plastic, it can be flexible, bendable. So it's different from LED. Okay, in this field, they're pioneers. All right, this guy, this person, Chin-Tan, he used to work for Eastman Kodak. Then he invented thin film type OLED. Okay, so he published a paper in 1987. So he initiated the field of organic LED. Then these two people also very famous. One of them he's a Nobel laureate, Alan Higar. They are polymer chemists. So they use kind of light emitting polymers to make OLED. So these three are very famous people. So 1987 is around here. This is the first paper, Professor Tan. He's now in Rochester. Also, he's moving to Hong Kong. He published a paper. The efficiency at that time was very low. Okay, here, 1 lumens per watt. Now, incandescent light bulb gives you like 15 lumens per watt. Now, so you know how low it is, right? But now, not now, about in the year 2000, the efficiency gets very, very high. Okay, here is the practical level of light emitting device here. Okay, incandescent light bulb today gives 15 lumens per watt, and fluorescent lamp like 80 to 90 lumens per watt. So OLED efficiency get to level of a practical level about 14, 15 years ago. So around that time, people are trying to make displays. Okay, how to make displays? It's very easy. If you look at your LCD monitor, particularly large TV, you will find red, green, blue dot, right? So if you can make LED, OLED, okay, this way, blue, green, red, tiny subpixels, you can make a TV. Oh, sorry. Uh-oh. This is my daughter in Hawaii several years ago. Oh, yeah. So around this time, in 1997, actually, the first product of OLED, okay, came from Yonezawa. So in our city, there is a company, Pioneer, a speaker company. They first demonstrated OLED display and started manufacturing such a OLED display in 1997. At that time, it's a green, okay, very simple green, so-called passive type display. So actually, they manufacture this by hands. So no production line at that time. But in the year 2000, they installed the line, it's automated. So they really mass-produced this kind of display for their car audio and also cell phones for Motorola. And next, it's a kind of color display, but passive type. NEC Samsung, they have the company together. Sanyo, Sony. The displays are so-called active type. Okay, this is a TFT OLED. So it becomes full color and high resolution. So you can see, starting from 1997 to 2004 or 5, okay, those displays have been commercialized and getting larger. And today, you have cell phone, not only cell phone, you have a smartphone. Okay, Galaxy, it's OLED. I think maybe many of you use Galaxy cell phone and smartphone. It's OLED. Also, Galaxy tablet, OLED. And the Sony introduced small size TV several years ago. So many products now carries OLED because it picture quality is better than LCD. Also, it's much thinner than LCD. Also, power consumption is smaller than LCD. All right, now it's become bendable, and in the future, it's become rollable. So OLED TV demonstrated by Samsung last year, 2 years ago, a 55-inch. But the problem is, mass production of large-size TV is difficult. This is the reason. Okay, this is a G10 glass substrate. You know how large it is. It's 3 meter by 3 meter. Okay, to make large-size TV, you have to use this kind of extremely large substrate. And Samsung used shadow mask technique. Okay, shadow mask looks like this. Okay, you had to deposit blue, green, red, one by one, moving shadow mask. Okay, the problem is this is very tiny. So alignment has to be like plus minus 3 micron. Okay, this is 3 meter by 3 meter. Also, when you vacuum deposit organic materials, okay, you have to heat up crucible. So you have to also warm up the substrate. So substrate, not substrate, shadow mask. Shadow mask is the metal, so it expands. Okay, easily 50, 60, 100 micron expand. So alignment of plus minus 3 micron is very difficult. So it often or easily create some defect. Okay, so people in Kodak and Sanyo proposed color filter technology. Okay, not just color filter, but also 4 pixel formats. Okay, I showed you you need red, green, blue. Okay, red, green, blue. So you have a white OLED and 3 kind of color filter. You can make a small pixel of red, green, blue. But the problem is, white color is a kind of very wide spectrum. Okay, and you use only red part, a green part, blue part. That means you are losing efficiency. So in this case, red, green, blue, white. Okay, you don't lose any light for white pixel. Now, actually, this is given by friend from Kodak. If you analyze, I think 1 million or pictures, okay, most of the color is white, and plus a little bit colors. So that means if you want to show this kind of color using blue, green, red pixels, this part is actually white. So if you have a white pixel, okay, emit white light and plus a little bit green, a little bit red. So this color is equal to this color. Okay, so this white is very efficient. So the panel efficiency can be very high. So using this kind of red, green, blue, white format, Sanyo display commercialized this kind of small OLED display. I think it was like 6 or 7 years ago. But unfortunately, Sanyo, actually there's no Sanyo company, okay, stopped OLED activity a long time ago. So LG bought patents from Kodak. So they started using this red, green, blue, white display. Okay, this is a 55-inch. It's in the market now. They demonstrated 77-inch large size display. So white OLED is extremely important in display business now. How large it could be? Okay, this is a 155-inch display by Mitsubishi Electric and Pioneer. Actually, in this case, they use our so-called tiling technology. Tiling means they have like one unit like this, 10 centimeter by 10 centimeter unit. They simply put a lot of them. In this case, 720 tiles. So they can make it very large. So it's not limited to 155. You can make 300-inch TV or much larger than that. If you have a chance to go to Japan, maybe you are landing at Narita Airport. There is a huge display there. This is OLED. Narita, I think, Daiichi Terminal or something. Okay, you can take a look at it. So OLED can be very large. Also, OLED can be very small. Okay, this is a head-mount display sold by Sony. Okay, in this case, you have 2 displays just in front of your eyes. Very small. Okay, 0.7 inch. Number pixel is 1,280 by 720. Okay, very high resolution. Because it's a very high resolution, you cannot use shadow mask. Okay, so you have to use a white OLED, you have to put color filter there. So even for this kind of tiny display, you need a white OLED. All right, the next step, as I said to you, it could be flexible. So people are now working on flexible displays. Okay, long time ago, we actually worked on flexible display together with Dai Nippon Printing and also Pioneer, and demonstrated this kind of displays by gravure printing technique. This is a vacuum deposition, but it's a passive type display. The difference between glass substrate and plastic substrate is the plastic substrate, moisture can penetrate, and OLED is very sensitive to moisture. So you have to do something. You need a kind of barrier coating on plastic substrate. Okay, this is a glass substrate, ITO, OLED, organic layers, and metal cathode. Okay, usually we put a metal can or a glass cap. To be flexible, of course, you cannot use this kind of metal things. Okay, plastic, you have to put one layer, barrier coating by chemical vapor deposition. On top of it, we deposit again such a passivation layer. Okay, this is silicon nitride layer. So we made this kind of passive type color display. Sony also demonstrated this kind of color display. And these days, okay, this is Sony's organic transistor driven OLED display, the most advanced display in the world. Okay, very, very flexible. It's rollable. And Samsung is going to manufacture this kind of a display, I think maybe in a couple of years. Not only Samsung, but LG, also Taiwanese company AUO, they already demonstrated this kind of a flexible OLED display at SID this year. So they're going to manufacture this in a couple of years. So your cell phone could be bendable in the future. So what the state of the art of white OLED? Okay. To get white light, people say, you use a white emitting material, okay, sandwich, it's done. But the thing is not that easy. Okay, there's no white emitting material. So we had to combine, for example, blue, green, red emitter. Okay, you can maybe stack or you can mix, then you can get white light. So it was about 20 years ago, we published a paper, white OLED. As Bernardo said, efficiency was less than 1 lumens per watt. And the lifetime was like maybe 3 minutes. So it's not useful at all. Of course, I wrote in the paper it could be useful for lighting application in the future, but it's very low. Everything is low. And before the science paper, we published a paper using a polymer. Okay, a polymer polyvinyl carbazole. This is very known for transporting p-type polymers, existing long time. And I think this is a blue emitting. Okay, I'm a polymer chemist, so I wanted to use some kind of polymers. So polymers, and we disperse some kind of organic dyes. Okay, red, green, blue, yellow, a lot of dyes. Then spin cast. Okay, on top of it, we deposit, vacuum deposited N-type small molecules. So this is a kind of hybrid. Okay, solution process and vacuum deposition, polymer, small molecule together. So we get white light. Then next is vacuum deposition. Okay, we cannot mix a lot of colors in vacuum deposition. So we have to stack like this. Okay, the key technology here, if you simply stack, you cannot balance red, green, blue. So you have to tune each intensity of each color. For example, this TPD molecule is a blue emitting material, LQ is green emitting material. If you simply stack two materials together, you get green light. You don't get blue. But we found out if you put very thin layer of triazole with a very deep HOMO level, we call it the hole blocking layer. You can block holes go into the LQ. But if it is thin, you can really control the amount of holes going into the LQ layer. So we can get blue, green, and we put a very thin layer of night red somewhere, so we can add red, so we can get white light. So the performance was so poor 20 years ago, but people got interested. So it used to be like display companies working on OLED, but lighting companies got interested and came to us. Okay, Professor Kido, if you can get the efficiency 15 lumens per watt, that's the efficiency of incandescent light bulb. Also, lifetime 3,000 hours, we can commercialize it. So we worked very, very hard. It took about 10 years to get this point. Okay, new compounds, new device structure, whatever. So I thought those companies can produce or manufacture. Okay, but those guys said, "Oh, Professor, 15 lumens per watt is no longer high enough. Okay, we need 100 lumens per watt because LED coming out. LED is so efficient." Okay, so we had to get 100 lumens per watt. Now actually our target is 200 lumens per watt because we already reached 100 lumens per watt. Okay, lifetime, okay, stability, it has to be like 30,000 hours. And luminance level, initial luminance has to be like 5,000 candles per square meter. Has to be very, very bright. And CRI is a color rendering index, has to be more than 90. These are the numbers we are targeting. Okay, to reach to these numbers, what we have to do, what we are doing. Okay, this is conventional OLED, okay? Glass substrate, ITO, okay, transparent electrode, organic layers, metal. Okay, then we used to use a fluorescence emitter. Okay, fluorescence. If you use fluorescence, okay, charge recombination generate singlet and triplet excited state. And if you use the fluorescence emitter, you use only the singlet excited state. Okay, so our internal quantum efficiency can be only 25%. Also, light out coupling efficiency, okay, because refractive index of organic layer is very high. Okay, so light out coupling is only limited to 30%. Okay, so our external quantum efficiency using fluorescence material is limited to 5 to 7%. Okay, we are losing a lot of photons somewhere. Okay, power efficiency of white could be like maybe 10 lumens per watt. Okay, so we have to move from fluorescence to phosphorescence. Okay, we have to use all the excited energy there. Also, we have to reduce the driving voltage. Okay, even you have a high quantum efficiency, but your driving voltage is high. That means your power is very high. So you have to reduce the driving voltage. So you have to develop a very good transporting materials. Also, we have to work on those interfaces. Okay, injection barrier height has to be 0. Also, you have to work on light out coupling. Okay, if you do everything all together, the EQE could be more than 60%. Or now, actually, already demonstrated 60%. We are now looking for a number like 80 or 90%. Power efficiency could be 200 lumens per watt. So we ran a lot of national projects in Yamagata University. This is one of the largest ones. I was the project leader from 2002 to 2006. It's about 5 years project. We spent like $50 million, a lot of money. Our target is a large OLED display over 16 inch. And also, we had to develop organic transistors. So what we did, or what we are doing, is we had to develop new materials. So we need chemistry. So we have a big chemistry lab. About 30 to 40 people can synthesize materials there. The characterization, fabrication of OLED. This is the first screening, so we have a lot of small evaporators there, many. Also, we have a clean room, so we have kind of cluster tools, okay, fancy tools. Then we had to evaluate lifetime. So we do everything in this field. So the efficiency of OLED had been improved during that 5 years. Okay, this is before, okay, using fluorescent materials, like 15 lumens per watt, it was maximum. During NEDO project, using phosphorescence, the efficiency went up and up and up. Okay, in the year 2008, the efficiency became like 70 lumens per watt. Okay, toward 200 lumens per watt, what we do, first we talk about EQE, external quantum efficiency. As I said, we had to move from fluorescence to phosphorescence. Okay, this is typical fluorescence emitter, coumarin 6, you can buy from Aldrich. Okay, this is phosphorescence emitter. This is kind of metal complex, okay, the iridium complex. There are many compounds already developed and sold, okay, green, yellow, red, very good emitters are already available. But the problem is blue. Okay, there is no perfect blue emitter yet. Okay, there are blue, for example, and the problem is, for example, this guy we call it Fairpick. This is the efficiency is very high. The internal quantum efficiency can be 100%. But the problem is the blue is not really not pure blue. Okay, this is kind of sky blue. We need a pure blue, nice blue. Also, the lifetime, okay, stability is not very high. Okay, this one degrades very easily. But this compound, okay, this is emit at 444 nanometer. It's a nice blue, but the efficiency is not very high. So we need a perfect blue compound. Also, you need a good transporting material for blue. Okay, hot transporter, okay, P-type, electron transporter, N-type, the host, okay, for blue. So we have to synthesize all compounds required. We synthesized more than 300 compounds during 5 years project. And this is, I think, one of them. Okay, the synthesis itself is very simple. Okay, first we have to design the molecule. Okay, to have a high T1 level. Okay, then electron transporting ability, whatever. Then we had to buy reagent. Okay, then synthesize the two-step reaction. The important thing is purification. Okay, this is semiconducting material, semiconductor. It has to be very pure. So you had to purify, by many process. All right. The interesting thing is, okay, these three compounds, okay, very similar. If you're not chemist, you don't see the difference at all. But we are chemists. You can tell the difference. Okay, here, the position of the nitrogen. Okay, it's a four position, 3 and 2 position. Okay, the other are the same. But if you measure the mobility, okay, electron mobility, they are so much different. It's the B2 here, B3, B4. Okay, about 100 times higher, this one, compared to B2. And the difference is only the position of the nitrogen. Why? Okay, we look at that morphology or the film, okay, vacuum deposited film, okay, by ellipsometry. Okay, you measure refractive index, okay, perpendicular to the substrate, parallel to the substrate. Okay, this B2 case, very similar, maybe no difference. But in case of B3, B4, there's a big difference here. That means the molecules are kind of oriented, okay, like this. It's not crystalline film, kind of amorphous, but oriented. Because I have nitrogen here or there. They could form a hydrogen bonding like this, so that they're like shaking hands. Okay, so they can orient. So that position of nitrogen has to be 3 or 4. So once you get such a good material, okay, OLED performance get improved. Okay, this is our white OLED. Okay, this is orange, green, blue emitters, and the new kind of electron transporting material. Okay, this is spectrum, and you can see here the external quantum efficiency can be 22 or 23%, and in lumens per watt, efficiency is like about 50 lumens per watt. Okay, 50 lumens per watt without optical outcoupling technique means if you do something like putting some light outcoupling film or whatever, okay, you can get 100 lumens per watt efficiency. 100 lumens per watt means okay, the efficiency larger than fluorescent lamp. So this table summarizes our OLED performance using phosphorescence emitters. Okay, green, orange, you can get very high numbers like 29%, 25%, and sky blue with ferropic, we can get 30% efficiency. So 30% external quantum efficiency means 100% internal quantum efficiency. That means you can convert one electron to one photon. Okay, with optical outcoupling techniques, you can get very high numbers in lumens per watt. Okay, 266 lumens per watt green OLED. This means this number is actually larger than that of LED. Okay, so the OLED performance is really getting higher and higher. Okay, then the important thing is reducing driving voltage. Okay, you get almost 100% quantum efficiency. So what we do next is reduce driving voltage. As I said, you have to work on interfaces. Okay, cathode interface, anode interface, and also those transporting materials. Okay, in case of cathode, there are many papers, okay, reported on these cathode material itself or interface layers. Okay, and we reported 1993. If you put very thin layer of lithium, okay, you can reduce the driving voltage. Okay, also lithium quinoline, lithium DPM, lithium metal complex. Okay, thin film. If you insert, also you can reduce the driving voltage. Also, if you dope organic layer with lithium or cesium, those reactive metals, you can also reduce the driving voltage. In case of lithium fluoride or lithium oxide, okay, these are very, these are insulating material. But if you make it very thin, okay, it works like an electron injection layer. Okay, the reason we think is very simple. Okay, lithium fluoride, a very thin layer on top of organic layer. If you deposit aluminum, okay, aluminum reduce lithium ion to lithium metal. Okay, then lithium metal reacts with ALQ, for example. So at the surface on ALQ, it's okay, doped. So we optimized those are electron injection layer, electron transporting layer, like this. Okay, lithium quinoline, lithium BPP, or new type of electron transporting materials. You see the big difference. Okay, they look very similar, but makes big differences here. Okay, so combination of lithium BPP and B4PY PPM gives very low driving voltage. And we optimize the device structure like this. Okay, this is HOMO-LUMO levels. Okay, so the kind of a stepwise injection makes a lower driving voltage. The important thing is here. Okay, we call turn-on voltage. Okay, when you get 1 candle per square meter. Okay, in case of this blue plot here, so in this combination, turn-on voltage is only 1.97 volt. Okay, 1 candela, quantum efficiency is 20, maybe 3%, so almost 100% internal quantum efficiency. The important thing is this emission is green. Okay, this is the spectrum. Okay, the peak wavelength is here, 523 nanometer. The photon energy is 2.38 eV, but we get this photon at the voltage of 1.97 volt. Okay, so below the photon energy you can getting green light. So we cannot explain why, but this kind of thing never happened in LED, only happens in OLED. So OLED, driving voltage can be very, very low. It's below the theoretic, driving voltage. Okay, long lifetime at high luminance. That's required for lighting. Okay, this is typical performance of OLED. Okay, if the luminance goes higher, the lifetime gets shorter. Of course, you have to inject a lot of current there. Also, efficiency in lumens power decreases like this. For display applications, it's okay because display is not very, bright. You look at it directly. But for lighting, okay, you have to shine something. So luminance has to be about 10 times higher. So if you use the same white OLED used for small size display for lighting, it dies very quickly. So we need the device performance like this. Even at high luminance level, it maintains long lifetime. So we developed so-called multiphoton device. Okay, this is actually the tandem structure. Okay, very simple idea. If you stack 2 OLED unit, okay, the same current density, you get double luminance. Also, you can mix the color like this way. Sky blue unit, orange unit, you can get white. So in the year 2003, a little more than 10 years ago, we reported this kind of new tandem structure at SID, Society for Information Display. This is the first time, okay, very bright white OLED was, performed. So this day we use phosphorescence. Okay, this is 2 units phosphorescence green, 3 units phosphorescence green. I told you using phosphorescence, you can get 100% internal quantum efficiency. Okay, in this case, this is external quantum efficiency. Okay, 1 unit, 2 unit, 3 unit. 3 unit, you get about 60-some% external quantum efficiency. That means about 220% internal quantum efficiency. So by calculation, you inject 1 electron there, you generate 2.2 photons there. So using this kind of technique, to drive OLED at high luminance level, it requires very small current. That means even at high luminance level, the device lifetime can be very long. So we have very good OLED. We worked on commercialization. Okay, Yamagata Prefecture okay, people there get very much interested in OLED technology, so they want to activate industry there by OLED. Okay, so they spent like $43 million, 7-year project. So I became like a director there. We set up a research institute for organic electronics there. Also, Japanese government supported to develop OLED lighting panels for 9 years. So about 10 years ago, we demonstrated this kind of very large size white OLED panel for the first time. And at the lighting fair in Tokyo in 2005, we demonstrated this kind of OLED luminaire. Okay, this is the first OLED luminaire demonstrated in the world. 2010, we went to Frankfurt to demonstrate newest panels there. In 2008, I started the company together with Mitsubishi Heavy Industry, ROM. This is a semiconductor company, Toppan Printing, and Mitsui company. So 4 company, 1 person started panel company, Lumiotech. And the factory, main office is in Yonizawa. Now they have a small pilot plant. They can handle 30 centimeter by 30 centimeter glass substrate. And in the future, we have to have a very big line like this. So we have to handle like a 1 meter by 1 meter glass substrate. We calculated if we use such a large size glass and 1 minute takt time, we can really reduce the cost. Okay, maybe 1 meter by 1 meter panel at about $100 or something. So the size of this could be like, I think, less than $10 in the future. So in the year 2011, we started small scale production, and 2 kinds of white OLED panels are now sold. Okay, this kind of warm white and cool white, 2 kinds. And our collaborators, like Panasonic and NLC Lighting, they have kept doing R&D, and they demonstrated the panel with the high efficiency, like 110 lumens per watt last year. Also NLC Lighting, 75 lumens per watt. And OLED cell, okay, but 1 centimeter by 1 centimeter OLED cell, they demonstrate 156 lumens per watt. So it's getting close to 200 now. Also, our collaborator, Konica Minolta, they actually invested $100 million this year. They are now building a big factory there. So in the future, if they start large production in large volume, I think the panel price will really drop. I also started a company, luminaire company, okay, Organic Lighting Corporation, so that we buy panels from Lumiotech, then we can make such a luminaire and sell. Okay, so in Yamagata Prefecture, if you come, okay, you can see OLED lighting fixtures, not everywhere, but in many places. Okay, so in the restaurant, fruit shop, this is my office, the governor's office, wherever you go, there are OLEDs. Even in Tokyo area, some museums use OLED. Okay, so OLED luminaires are getting popular in Japan. So what's coming next, or what we are doing? Okay, printed white OLED. Okay, we've been using vacuum deposition. So our vacuum deposition tool is big, okay, bigger than this room. So you had to pay like $50 million for 1 line. Okay, so also you had to have a clean room. So to reduce the cost production cost further, okay, like this size, maybe $3 or something. You have to use kind of a roll-to-roll printing method. So we proposed to Japanese government. They funded us 10 years project. Okay, so we worked together with Dai Nippon Printing and Konica Minolta together to develop, all printed OLED. Okay, to make such a printed device, we had to develop, printable materials. They are different from small, more conventional materials. Okay, these are the requirements. Okay, solubility, it has to be soluble in solvent, of course. They had to form a nice film. Okay, high thermal stability. Okay, high electrochemical stability. Okay, high carrier mobility. Okay, high triply excited energy level. Appropriate homo-lumo levels. This is just one of the examples. Okay. So people think about polymers, but I'm a polymer chemist. I know polymer is not simple. Okay, this is polyvinyl carbazole. Okay, this is one of the repeating units. But polymers, they have a molecular weight distributions, and sometimes they have a defect in the main chain, defect or end group, whatever. Okay, so it's very difficult to purify polymers. So we are moving from polymer to small molecule. Okay, so this is a carbazole containing polymer, carbazole containing small molecule. This is very soluble. But if it's too soluble, it's very difficult to make a layered structure. Okay, for example, this is a polyvinyl carbazole. You spin cast, bake it, rinse it with methanol. There's no difference. Okay, not soluble in methanol. But in case of CBP, this guy vacuum deposit, making a thin film, rinse it with methanol, it's gone. Okay, so if you spin cast something on top of it with methanol solution, it's gone. Okay, so we have to check. Okay, is there any molecular weight? Okay, it becomes insoluble in methanol. Okay, this is CBP molecular weight 484, PVK typically 75,000. Okay, where? We check 17 compounds. Okay, containing carbazole groups. Okay, from number 1 to number 17. Of course, some of them are commercially available, but these are the compound my student synthesized. And we checked. It's very interesting. Okay, first we make a thin film, then rinse it with methanol. And the y-axis is normalized remaining thickness. Okay, the molecular weight over 800, it remains there. Okay, even it's a small molecule, but molecular weight smaller than this. Okay, it's gone, soluble. So as a 90% remaining thickness, we just named it threshold molecular weight. In this case, 767. Okay. We check several solvent, different kind of alcohol, ethanol, 1-propanol, 2-propanol, very similar behavior. Okay, so threshold molecular weight is like maybe about 800. So we can make this kind of device. Okay, 4-layer structure. Okay, PSS. This is conducting polymer. Kind of a water solution, a dispersion, spin cast, bake it. On top of it, using paraxylene solution. Okay, this TFB, this is a real-amine containing polymer, spin cast, bake it. On top of it, okay, using diethoxy ethane solvent. This is emitting layer. Okay, 2 kinds of host, 3 kinds of emitters, spin cast, and bake it. Because it's not soluble in propanol, we can spin cast this electron transporting layer by two-propanol solution. Okay. Then vacuum deposited lithium, Q, and aluminum. So 4 layers, okay, stacked by solution process. So we get this kind of spectrum. This is white, and efficiency is 34 lumens per watt. EQE 21%. We're getting close to vacuum deposited OLED. So using our optical light out coupling, you can get 76 lumens per watt. 76 is the efficiency of a fluorescent lamp. So using simple solution process, you can get this kind of efficiency now. So our next step is to make a multiphoton device. Okay, this is very difficult. This is very challenging. Okay, this is, for example, two-stack multiphoton device using polymer layer. But in this case, this is a kind of connecting unit is aluminum, moly oxide, vacuum deposited. Okay, you had to use something solution processable like this. Actually, we found this kind of system. Okay, there are many layers. I don't know, maybe 8 or 9 or 10 layers. Okay, starting with water, dispersion, paraxylene, 2-ethoxyethanol, 2-ethoxyethanol, acetonitrile, chlorobenzene, butyl acetate, methanol. Okay, using so-called orthogonal solvent systems. You can make many layers on top of each other. So this is the white OLED. Okay, this is the first unit. The second unit, the multiphoton structure gives just double the voltage. Okay, this is the first unit, second unit. If the summation of those plot become like a multiphoton performance. So it becomes the white. So this is the efficiency roadmap for white OLEDs. Okay, using vacuum process. Now in the laboratory level, it became like already like 150. So in a few years, I think we can get 200 lumens per watt. Now factory level. Okay, now Lumiotech is selling 60 lumens per watt panel. It soon become like 100. Soon become 150. Then in the future, 200 lumens per watt. Very efficient. And printed, okay, come later. Okay, now actually nobody is selling printed OLED. Okay, but in several years, I think Konica Minolta or Nippon Printing will start selling like maybe 30 or 40 lumens per watt panel by roll to roll or something. So in 10 years, I think both systems will be sold. Okay, high performance OLED by vacuum deposition, and lower performance but much lower cost. Okay, much lower price OLED by roll to roll. So I want to introduce to you our university activity. Okay, in the year 2011, we started a research center called the Research Center for Organic Electronics. This is a 5-story building. Total floor area is like 5,600 square meter. So each floor is like a little bit more than 1,000 square meter. So each floor is dedicated to each technology, like OLED, OTFT, OPV. Okay, so I'm here on the 5th floor, and part of 4th floor is also OLED. Also, there is another building here on the 1st floor. I think it's about 800 square meter is OLED. So these days we don't. Okay, we are not just OLED people. There are people working on OPV, OTFT. Also, we started another center called the Innovation Center for Organic Electronics here. Then this is the place we work on something practical, okay, application, panels, modules. So we hire people from, for example, Pioneer, Sharp, Konica Minolta, Luminotech. So these people are now working as a professor in our university to develop printing techniques or printed devices, some modules. Okay, so for example, this is a portable OLED. Okay, usually you need some kind of cable there and connect. But in this case, in the back of the panel, there is a very thin battery there, and also circuit there, so you can bring it anywhere. Also, this panel in front of glass, there is a Japanese paper, traditional paper there, so it looks like a kind of a nice Japanese style lamp. Also, this guy, he has a kind of a band. Okay. So it's kind of sensing. I don't know what the mechanism, but depending on how he feels, the color of OLED changes. Okay, so if you are angry, maybe it becomes blue or something. Okay, to cool you down. If you're down, it becomes red to activate you. Something like this. So we work on something, such as applications, panels, modules. Also, we can make a kind of, flexible OPV. Okay, semi-transparent, very fancy OPV. Or transistors, not just transistors. We are working on arrays. Okay, so this is integrated organic transistors, and especially this one is a flexible, not only flexible. These transistor arrays are made by printing techniques. Okay, so their technology. Actually, we hired Professor Tokito from NHK lab. So he has a big group working on transistors. So someday we combine to make a big, flexible OLED. We are now constructing another building. So we will start another center here, Frontier Organic System R&D Center or something. And what we are going to develop is something like this. Okay, now in industry, people are going to manufacture small size, OLED display, flexible. We're going to develop 120-inch flexible OLED display. And this display is not just display. This is kind of interactive. Okay, so people can communicate through this wallpaper to friends or parents or sons, daughters, wherever. Okay, also the lamp is not just white. Okay, sometimes it's like a blue sky and white cloud. Okay, sometimes it's a dark night. Sometimes it's like a storm coming, whatever. Okay, so it could be like Hawaii Island. You're Hawaii Island. Okay, this is, I heard in winter time it's cold here, right? So you want to feel like you're in Hawaii. You can want to relax because you work in a lab for, I don't know, 18 hours a day or something. If you go back, you want to relax, right? So, so this kind of application or this kind of panel, very useful. So, but if it's expensive, nobody can use. So we had to develop printable OLED, okay? Printable TFT backplane, low-cost plastic barrier film. If we have these things all together, we can really realize this kind of OLED panels. Also, we are building a small house. Okay, we named it Smart Future House. Okay, and inside there are, we put the advanced technologies, organic technologies there. As I said, the wall is display, and ceiling display. You can really feel, what kind of feeling you have if you have Hawaii there. Okay, then of course lamps are all OLED. Okay, So we're thinking about what kind of bedroom should supposed to be. Okay, what kind of kitchen in the future we should have. So we can experience new things there. So in Yamagata Prefecture, as I said, we are surrounded by mountains, lots of trees, lots of fruits. But not only those things, we have OLED. Not only OLED, we have transistors and solar cells, many new technologies there. So 26 years ago, actually there was nothing there. I started from just one flask, and now there are 3 buildings coming, and 1 smart house will be built. And OLED display company, Pioneer, still there. They actually started a lighting company, and I started Lumiotech there, and there are a couple of startup companies. So from really scratch, okay, if you work hard, okay, within 20 or 30 years, we can really make something. All right, I have to thank my students, postdocs, colleagues for their very hard work. I don't know, is that here? We're here? No? Maybe you are in the lab working. Okay, you're a hard worker. Also, thank you very much for your attention.
Very much. We have time for some questions.
One question. Are all your devices made with ITO?
Oh, yes.
So isn't ITO pretty expensive and in limited supply?
Yes, very good question. So we have a project, flexible plastic substrate and barrier coating on top. We are going to have a transparent electrode. Okay, not ITO.
Injection layers.
Yes.
It looked like on one of the hole injection sides you had CN6.
Oh, yes.
I just wondered if what do you think the role that is there?
Oh, the role of HCN. Well, HCN, it has very low lumo level. So you cannot inject holes there, right? So from ITO, you don't inject holes there. But HCN has very low lumo level, and on top of it, you have acrylamide. This one has very shallow HOMO level. So at the interface, they generate charges. Okay, so from HOMO level of acrylamide, the electron moves to the lumo level of HCN. So you can form positive and negative charges there. So that means injection of holes occurs at the interface between HCN and acrylamide. Yeah, it's a charge generation. It's not conventional hole injection layer.
Question there, Matt?
You mentioned that you want to keep water vapor out of them. Do you also have to keep oxygen out of them or protect them from photooxidation as well?
I think oxygen is not as bad as water. For example, those display panel, they have a metal can there, right? They used to have 100% nitrogen inside, but these days they put small amount of oxygen there. The reason is if you have a short circuit somewhere, you simply bias and reversely, so that you have a fix such a leakage or a short circuit, oxidizing aluminum electrode. So oxygen itself may not be so bad.
You mentioned that you're creating a 120-inch flexible display.
Yes.
Do you need the flexibility in the application, or is it coming from manufacturing and the local?
Oh, well, if you use a glass, we live in very small house, so you cannot bring in 120-inch huge display. Also, it's very heavy. So lightweight, and maybe bendable has to be, must be required. Yes.
I was wondering, along that discussion about making large screens from tiles, what's the size where the tiling starts to be attractive? Why don't we make TVs with smaller tiles rather than trying to produce it on one large?
Well, it could be tiled. Yes. So Pioneer, they have only, passive displays there. So the size of passive is limited. So 10 centimeter, maybe the largest size they can offer. So they started using this kind of size. But for active, I think it could be larger. So for 120-inch flexible, maybe you can have maybe 30 centimeter by 30 centimeter tile. If it's small, it's a lot of labor required. Yeah.
All right. Any other questions? I guess people are getting ready for the reception. Oh, sorry.
Just a quick question. I saw different technologies, different kind of white OLEDs for different kind of purposes. But I saw one constant, the iridium complexes.
Oh yeah.
I know that the iridium is very, very rare material. At some point, it's not very competitive for the cost of the device. Are you thinking about using something else?
Yes, Professor Adachi at Kyushu University, he introduced new type of emitter called the TADF, thermally activated delayed fluorescence. It doesn't contain any heavy metal. So in the future, maybe we don't use iridium complex. Also, if you think about display applications, and the amount of iridium complex used is very small. First of all, also display requires backplane, circuit. Those are very expensive. So even you don't use iridium complex there, the price of the display cannot be half or something. Maybe a little bit reduction. Yes, but for white OLED, okay, the cost comes from the material itself. So better not to use iridium.
Okay, well, before we thank our speaker, we have a tradition here. And so all the distinguished guests for the seminar series, we don't let them go without a little souvenir.
Wow.
And so don't worry, you won't have to try to fit it in your suitcase. But anyway, hopefully you'll find some space in your office to
yes.
put a little. So let's thank Professor Kido one more time.
Thank you. Thank you very much.